Hello, I am Sam and this is my video presentation for Lab 4 Oscillations for the Physics 2211 course. The purpose of this lab was to explore the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring, and inside this lab I was able to successfully track the motion of the mass and created a computational model for the oscillating spring that closely matched the experimental results. So we're going to begin with some assumptions. We're assuming no damping, no friction, no air resistance, that the spring is massless in obeys Hooke's law, no temperature changes, no rotation of the mass, and no external forces. So for the provided video, we can have a mass dangling from a helical spring suspended against a light colored backdrop and a camera filming from some distance away. We define the system as the mass plus the spring and everything else as the surroundings. So here are the initial conditions describing the equilibrium length of the spring, the mass, as well as the spring constant, and these are given in a lecture video. And additionally, we also found through tracker the initial position of the mass, and we know that there are no initial velocity. So here is the theoretical model. We can find that the F net experienced by the mass is equal to the force of gravity plus the force of the spring, and we can then derive a vector expression for this net force. And here is the provided video for this lab. And from this video, I used tracker to calibrate the axis and the distance, and then use the auto tracker to track the mass over the period of time and its x and y positions. And here is the raw data that I obtained. So by using some calculations of like velocities and positions, I was able to calculate different energies and eventually find the total energy of the system. Note that the potential energy is in this calculation is negative because I defined the origin as h equals 0, and so for the entirety of the experiments the h is actually negative here. And for the code that I written for the computational model, I first used the mass of the ball, the initial positions, as well as a spring constant. I used the equation of the relaxed length as equal to the equilibrium length minus mg over the spring constant. And then here is my time calculations. And then I used the position update formula to calculate the mass's new position here. And then I calculated the different energies of the system. And then I printed the information of the different energies and the different characteristics of the systems for every single frame. So here is the video of the computational model that I obtained. And here is the data that I obtained from the computational model. So by combining them into graphs, we can see here is the x position of the mass compared to the time. Here is the y position of the mass compared to the time, and here's the deviation of the spring from the relaxed length compared to the time. You can see that both the experimental and the computational models agree very closely with one another. Here is the speed of the mass compared to the time, and then here is the calculation of the energies of the system versus time, with the green line being the total experimental energy, and here is the computational model as well. And by seeing the total energy of the system together, we can find that the computational model and the experimental model agree relatively closely from one another. So here we can see that the data of both models again closely agree with one another quantitatively, and that both demonstrate a regular oscillation of the mass about both the x and y axis. And first of all, we can find that the energy is conserved throughout the experiment for both of the models, and that the energy might be transformed, but the total energy remains the same. Though over time, we should expect the total energy of the system to decrease due to damping effects. And additionally, we can find that the computational periods of the oscillation are quite regular. For the y-axis, I found that the period is around equal to the period of the pure vertical oscillation of the same mass and spring. And for the x-axis, I found that the period is close to the period of a pendulum at the equilibrium length. So additionally, we also find that the computational periods of both axes seem to be slightly higher than the experimental periods. This might be caused by the accuracies from the assumptions, though it is actually the opposite of what I would initially expect, because the damping effect, which was not accounted for here, should actually increase the period of the oscillation. So I think it would be interesting to explore this area as well. So in conclusion, I was able to conduct a lab with the provided experimental model and the computational model, I found the expression to find the oscillation of the spring mass system about both the x and y axis, and I was able to create a computational model that very closely agrees with the experimental results. So here is the end, and thank you for listening.